Hello. In this video, I'm going to solve the following problem for you, which is a problem on the topic of division algorithm and number theory. Let P and Q be prime numbers greater than 3. Prove that P squared plus Q squared plus 13 is a composite number. In other words, we want to show that this number is not a prime number if P and Q are prime numbers greater than 3. That would be a good idea if you pause the video at this point and try to solve the problem yourself first. The interested student can refer to the following playlist for more videos of this type. The link of the PDF file that you see on the display now is in the description below the video. Okay, now let us start solving the problem. It's a very simple and standard way of thinking in number theory. So P and Q are prime numbers, both greater than 3. Okay, so here, this something you need to observe is that by division algorithm, let us consider this box to be the set of all integers. Then by division algorithm and choosing number 3, then this set can be partitioned into 3 distinct parts. That part is the numbers that are multiples of 3, and then 3 multiples of 3 plus 1 or multiples of 3 plus 2. So these are the only possibilities for an integer. Okay, but because P and Q are prime numbers, there is only one prime number in this first floor. Yes, I would call it. Because if I choose K1, then it becomes 3, and 3 is a prime number. But any other prime number cannot be here, because you yourself say that any number that's a multiple of 3 is here, and you know that for being a prime, this cannot be a multiple of 3. The only multiple of 3 which is indeed prime is just 3. And this is excluded because the problem tells you that P and Q are prime numbers greater than 3. Okay, so let me write something in general. So I would say let M be a prime number greater than 3. Then what happens? So that M cannot go here. M cannot go there. So it means that M is either here or here. I want to know something about the square of a prime number greater than 3. So if M is a prime number greater than 3, then it means that M, so either M is equal to 3k plus 1 or M is equal to 3k plus 2 by division algorithm for some integer k. Okay? If M is in this form, so let us understand a little bit about the square, because a square of those numbers are involved. So I square it, it becomes M squared is equal to 3k plus 1 squared. It becomes the first one squared times the second one, 2 times the first one times the second one, and then the second one squared. But between these two, I can factor a 3 out. Then I will have 3k squared plus 2k, yes? And then I have plus 1. But k is an integer, so this combination is definitely an integer. So let me call it capital K. And capital K is an integer. So it becomes 3 capital K plus 1. So what did I show? I showed that if M is any integer, not just a prime integer, if M is an integer in this floor, it means that it takes this form. Its squares will also take the same form. So if you pick up any number from this floor, for example, let me choose K to be 2, then this is 7. And then 7 squared is 49. 49 is also here, because it is 3 times 16 plus 1. Yes? But now what happens if M is not here, but M is there? So it means that if M is 3k plus 1 plus 2, then what happens? I will square it again. it becomes 3k plus 2 to the power of 2. The first one squared, 9k squared, 2 times the first one times the second one is 12k, and then finally plus 4 this time. But then instead of 4, these are standard techniques in number theory, yes? So I can write it as 3 plus 1, and then between these three, I can factor a 3 out, so it becomes 3k squared plus 4k plus 1, and then plus 1. But what does it mean? Here again, it is an integer, so I can call it again, for example, k prime. And the k prime is an integer. So what did I show? I showed that again, this becomes multiple of 3 plus 1. So if m is not in this floor, it is either here or there, but in both cases, the square of that number is of this form, 3k plus 1. It's a multiple of, so if the number is here, its square is multiple of 3 plus 1. If the number is here, again, its square will go back into this floor, okay? Okay, so now p and q are prime numbers greater than 3. By this part of the problem, I understand that p and q cannot be here, so p and q are here. So if you want to do it case by case, you had to consider four scenarios: p here, q here, p here, q here, p here, q here, q here, p here, okay? But by this way, I'm just making it very simple. So I'm saying that, okay, no matter what p and q is, they are either here or there, but I showed that in any case, the square of them is here, okay? So p squared is of the form 3k plus 1, pq squared is also of the form 3k k prime plus 1, and then I want to have that combination. So instead of p squared, I put that. Instead of q squared, I put this. And then I have a 13 at the end. But what happens? It becomes 3k plus 3k prime. And then 1 plus 1 plus 13 is 15. And then I immediately realize that I can factor a 3 out. So it becomes k plus k prime plus 5. Okay. Of course, here k and k prime are natural numbers, because when you say I have a prime number, the prime number is by definition a natural number. So k and k prime are natural numbers, so this is a number definitely greater than, it's a positive number, okay? So it is 3 times a positive number greater than 1, okay? So this means that this number cannot be a prime number. In other words, it is definitely composite number because it's a multiple of 3. Yes? Okay. So that is the end of the problem. So I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.